Hello everyone. So till our last video, we have completed very basics of periodic table. Now in this video, we'll start with the atomic radius. In atomic radius, we will see the ionic radius, covalent radius, and van der Waals radius, and in last, metallic radius. In atomic radius, we have to mostly concentrate on ionic radius because the question will be from ionic radius only or covalent radius, but it metallic radius and van der Waals radius, they don't have much concepts. So now we will start the ionic radius. Ionic radius. The definition for ionic radius is radius of ion is called the ionic radius. The radius of ion is called ionic radius. Now in this, the question is, what is ion? Ion is formed after the gain or loss of electron. Okay. After gain or loss of electron. What is gain of electron? When an atom is gaining electron or getting more electron, that is called the gain of electron, and it forms anion because gain of electron. So when an atom is getting more electrons, it will form anion, and anion will have minus charge like F minus, Cl minus, O minus 2, and minus 3, like this. These are ions: fluorine ion, chlorine ion, oxygen ion, like this. So the fluorine here is having one more electron. That's why it is having the minus charge, because electron have minus charge. Now loss of electron. Cation. When an atom is losing an electron or two electron, it will form the cation, and it will have, that atom will have the plus charge like Fe plus 2, lead Pb plus 2, sodium plus Na plus, aluminium Al plus 3, like this. So this is anion, this is cation. Now we have to compare the radius of these ions. So these type of ion, these type of comparing we can have, and in comparing these type of ion will have four types of cases types. First one, when all cations are present. Second, when all anions are present. Then third and fourth. Four cases we will have. Second case, when all anions are present. When cation, anion and neutral atom is present. When we are comparing cations only, when we are comparing anions only. Third case, when we are comparing cations, anions and neutral atoms. And last one, compare size of element in periodic table, like in neutral only. Compare size of element in periodic. Wait, it's not coming in a screen, so I'll write it again. Fourth one. Compare. So now it's coming in a screen. Compare size of element in periodic table. This is a fourth case. So these all four cases we will see. First we will see when all the cations are present. Now the first case, first type, when all cations are present. So in this, the size of cation or the radius of cation is inversely proportional to the magnitude of charge. Magnitude of charge. This is true for if the element or the ion is formed of same atom. Ions are from the same atom elements. Fe plus 3, Fe plus 2 and Fe like this. So here all the cations are from ion only. So the size of cation here is inversely proportional to the magnitude of charge. Where is the highest charge? Plus 3, then 2, then 1. So the size of cation will be inversely reverse of this. Fe plus 1 will be the highest, then Fe plus 2 will be the highest, then Fe plus 3. Here question is why the Fe plus 3 is the small in size, why Fe plus 1 is big in size compared to the Fe plus 2 and Fe plus 3. Because the central, in an atom center, protons are there and which are attracting the outer electron to its swirl. So the outermost electron which proton is pulling inside, here these are less, and here these are, compared to this, it is more. Outermost electrons are more. So the force to the center plus an electron, for the first case this electron is attracting the proton, and proton is attracting, electrons are getting attracted to the center of atom. Okay, so this force is same always, but this force is changing as the number of electrons are changing. When more electrons are there, they can pull more outside, and so the size of cation will be more. So here less electrons are there, so it will pull less, so the size of cation will be less compared to the plus 1 and plus 2. Second, when all anions are present, the size of anion is directly proportional to the magnitude of anion charge. Of anion charge. Here the concept is same as the size of cation, because the more electrons are in orbit and it can pull more. So the as the size magnitude of anion is increasing, number of electrons are increasing in the shell, it will pull the, it will go outside, like, and the new proton cannot attract the electrons as it was attracting earlier. So the size of anion will increase to the directly proportional to magnitude of anion of charge. For example, carbon minus 2, carbon minus 4, carbon minus 3. Here C minus 2 will have the least size of anion, then C minus 3, then C minus 4. This will be the size of anion. And this is true for all the cases when ions are from same element. Now third case, when cation, anion and neutral is present. When cation, anion, neutral is present. For this, the concept is same as the earlier two cases. anion radius will be the highest or the big in size, then neutral radius, then last cation radius, cationic radius. The concept is same as we discussed in the last two cases. Neutral will have the more size than cations, and neutral will have the small size than anion. Anion size will be more than neutral. If you remember this image, you can remember this concept also, that the anion radius will be the highest compared to the cation and neutral, then neutral is more than cation, then cation is the last. If the cation, anion and neutral is of same atom or same element. Size of isoelectronic species. In this we will see one concept, size of isoelectronic species. Here iso means same and electronic means same electrons. So same electrons, when the species are having the same number of electrons. For example, Na plus and F minus. So sodium usually have 11 electrons. If we are forming the sodium cation, it will lose one electron, and total number of electrons then Na plus will be 10, and fluorine usually have 9 electron, and if it is gaining 1 electron it will count 10 electron. So in both the cases 10 electrons, 10 electrons. Electrons are same, so these are isoelectronic species. Or one more case we can see, calcium plus 2 and chlorine minus. Here the calcium have, neutral calcium atom will have 20 electrons, because right now it is having the plus 2 charge, so 18 electrons will be there. 18 electron, and here 18 electron, because chlorine have 17 electrons and this is Cl minus, so one more electron, 18 electrons only. This is also isoelectronic species. Now the comparison of size. In this case electrons are the same, but the protons, here 11 protons are there, and here 9 proton, here 20 protons, and for chlorine 17. So 11 protons are pulling 10 electrons to itwards. Here 9 protons are attracting 10 electrons, here 20, here 17. So in this case, first case, 11 protons are attracting 10 electrons and 9 protons are attracting 10 electrons. So which can pull more powerfully? 11, because here more electrons are pulling 10 electrons. So the size will be the less, where the in the isoelectronic species, when the protons Where the protons are more, the size will be less. So the size of isoelectronic species will be less because more protons are in Na plus. And for this, 20 protons are attracting 18 electrons and 17 protons are attracting 18 electrons. So this can pull more powerfully. So the size will be less. So this will be the isoelectronic species size of ions. Now we'll do an example here. Now we'll do the example N minus 3, O minus 2, F minus, Na plus. Here size will be all the ions are having the same. If you count it, all the ions are having the same number of electrons. Fluorine is having the 10 electrons. F minus is having 10 electrons. Sodium Na plus is having 10 electrons. Oxygen having 10 electrons, and nitrogen is also having 10 electrons. And protons 7, 8, 9 and 11. And one more we can write, neon, 10 electrons and 10 protons. Here the size order will be where the more protons are present, the size will be less because the number of electrons are same. So more protons are present in here, then here, then fluorine minus, then oxygen minus 2, then nitrogen minus 3. So Na plus will have the smaller size, then neon, then F minus, then O minus 2, then N minus 3. So this is very easy to understand. Now we'll go for the covalent radius. Covalent radius. In the covalent radius, what is the covalent bond we will discuss, then we will see the covalent radius. We will have two cases. First one, homoatomic atoms. Homoatomic. The second case, heteroatomic atoms. Homoatomic atoms, covalent bonded radius of atom like hydrogen H2, both the hydrogen atoms are having the same electron negativity, so they will have the covalent bond, and the radius of one hydrogen here will be the covalent radius of hydrogen when both atoms are same, because homoatomic means same atom. So the A, first atom is type A and second atom is also type A, and this distance If it is D, the covalent radius here will be covalent radius of A here we will count as a D, A to A, distance between both the atoms divided by 2. So that will be the radius of one atom, or the bond length also you can write bond length divided by 2. That will be the homoatomic radius, covalent radius. Now heteroatomic, case 1 here, case 1, two cases will be there. Case 1, if the electron negativity of atom, both the atoms are same. If electron negativity of both atom is same. For example, iodine, sulfur, carbon. Thus all three atoms or elements will have the same electron negativity. Then nitrogen and chlorine and hydrogen have same electron negativity as phosphorus. There is very small difference between electron negativity of these elements. So this is the one where the electron negativity will be same. The second, this you have to remember when you are solving, when you are getting problem like this, you have to remember this. The second case, when the electron negativity of both atom is not same. In this case, first case we will discuss first. In this case, it is very easy to calculate that covalent radius A, first atom, and V, second atom. This is bonded with the covalent bond. Now the distance between A and B will be RA and RB, and atomic radius, if you divide almost the if you divide distance between A and B with the with 2, the number you will get, that you can say is a atomic radius of that atom. Second case we'll see here. Case 2, this is for heteroatomic, this is also for heteroatomic. Case 2, if electron negativity of both atom is not same. In this case, we have a formula. From that formula, you can calculate the covalent radius. The formula is DAV is equal to RA plus RB minus 0.09 XA minus XB. This is a XA and XB is electron negativity difference. Electron negativity of first atom, then the electron minus electron negativity of second atom, and modulus of that electronegativity. We have to subtract from Ra plus Rb after multiplying with the 0.09. That will be the distance between atom A and B. From that we can calculate the covalent radius of atom A and atom B. This is difference of electron negativity. The last one is van der Waals radius. Second last. Van der Waals radius and metallic radius is not much important, but we will discuss this also, and then we will go for the very important and very conceptual atomic radius trend and periodic table. Van der Waals radius. Third, when gases are present in liquid form, the atoms is attracted to the other atom is the is attracted with the other atom with the van der Waals forces, and the radius when we are calculating in the liquid form of gases, that radius is called the van der Waals radius, and this is calculated between the molecules. Between molecules. So this is a one molecule of AB. This is a second molecule of AB. Like this. This is A, this is B, this is B, A. This is not drawn perfectly, so I'll draw it again. This is A, this is B. So these atoms are attracting, these molecules are attracting to each other with the van der Waals forces. So here in the first molecule B atom is attracted to the second molecule's B atom, and in this A atom of this molecule is attracting the A atom of next molecule, and this distance D B B D A A. Radius of B here will be distance of BB divided by 2, and radius of A will be distance of A divided by 2. This is all the concept in the van der Waals radius. Now metallic radius, fourth one. Metallic radius. In the metals, atoms are arranged in a form they can't move in space, so the distance between two atoms in solid form of any metal, this distance is called the metallic radius. This, if we divide with the 2 d, this d divide with the 2, that will be the radius of metallic radius of that element. metallic radius of A is equal to D by 2. This is all for the metallic radius. Now we'll see the atomic radius trend in periodic table. In periodic table, first super tricks here. Super trick for atomic radius. First we will see in period. In period of atomic radius or of periodic table, in period it decreases from left to right. Atomic radius decreases in period. Second, in group. In period, as we know that the Z effective, for this explanation is Z effective. In period, we know from left to right, Z effective is from left to right. Z effective is increasing, so the atomic radius will decrease. From this concept only, you can understand. It's easy to understand the atomic radius in period. Then group. In group, atomic radius increases in group. In a group from top to bottom, the orbits are increasing, as we know. In a next element in a group, the orbit one orbit is increasing, so the radius will increase. Although the Z effective is same, Z effective will be the same, but the because orbit or shell is increasing, so the atomic radius will increase. Now we'll see in periodic table trend. If you see in group G1, group 1, group 2, group 3, like this, group 4 to group 12, then group 13 to last group 13, 14, 15, 16, 17 and 18 last group. In first group, hydrogen, lithium, potassium, rubidium, cesium, francium. Atomic radius trend will be increasing, 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 increasing and increasing, because in group atomic radius top to bottom is increasing. Now in group 2 also this will be the same. Beryllium, magnesium, calcium, scandium, cesium, barium, radium. Here trend will be increasing, 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 and increasing. Now for the group 3, in a group 3, when you see scandium, then uridium, lanthanum, and actinium, atomic radius trend here will be the normal as groups, other groups. It will increase down, top to bottom it will increase. But after the group 4, the difference between atomic radius is not as much as it was earlier in earlier groups, because the lanthanide and actinide contraction, the radius will not increase as it was increasing before. So titanium, for group 4 zirconium, then HF, and group 5 vanadium, niobium, and Ta. So the atomic radius will increase, then here it's almost equal to the zirconium, and here also it will increase. So till group 12 zinc, till group 12 zinc, cadmium, mercury, this trend will be the same because of the lanthanide and actinide contraction. Okay, after group 12, the group 13, in group 13, this is a special case. In group 13, you can remember this as a special case. Top to bottom, we know that the radius is increasing, but because of the electrons are coming in d orbit and d subshell, so the because of dd contraction, the radius order here will be the opposite. So the boron will have the least atomic radius, but then this order will change, and the order here will be gallium, then aluminium, and then order will be here also same, indium, and because of lanthanide contraction, again this will be almost greater than equal to, sometimes it's, you can say equal also, or it's not increasing as it was increasing again before. So thallium. Now till group 18, helium, neon, argon, krypton, xenon, radon, the atomic radius order will be the normal, top to bottom will increase. So this all is the in the atomic radius order. Here, because of the lanthanide contraction, you can remember, because of the lanthanide contraction, the order is not increasing, and here because of DD contraction, order is not increasing, it's getting opposite. So this is all for the atomic radius concept. Now ionization energy concept, that heading we will see in the next video. Thank you.